You'll see, it's pretty easy to do. You've already seen height balance trees. AVL trees, for example, you keep the left and the right subtree that you want their height to be within an additive constant of each other, 1. Red-black trees are multiplicative factor 2. Left and right subtree, the heights will be roughly the same. Weight balance trees, weight is the number of nodes in a subtree. Weight balance trees, I want to keep the size of the left subtree and the size of the right subtree to be roughly the same. So here's the definition of VB alpha trees. For each node V, size of left subtree of V is at least alpha times the size of V, and size of the right subtree of V is at least alpha times the size of V. Now, size, I didn't define size. It could be the total number of nodes in the subtree. It could be the number of leaves in the subtree. Doesn't really matter. What else? What's alpha? If alpha is a half, you're in trouble because then it has to be perfectly balanced. But if you just make alpha small, like a tenth or something, any constant less than a half will do. And right, the nice thing about weight balance is they imply height balance. If you have this property that neither your left nor your right subtree are too small, then you know as you go down, every time you take a left or right child, you throw away an alpha fraction of your nodes. So initially you have all the nodes. Every time you go down, you lose an alpha fraction. How many times can that happen? Log base alpha, basically. So log base 1 over alpha. So the height is log base 1 over alpha of n. So this is really a stronger property than height balance. It implies that your heights are good. So it implies the height of the left and the right subtree are not too far from each other. But it's a lot stronger. It lets you do updates lickety fast, basically. So how do we do an update? The idea is normally you insert a leaf, or do a regular BST insert a delete. You add a leaf at the bottom or delete a leaf. And so you have to update like that node and maybe its parent. As long as you have weight balance, you're just making little constant size changes at the bottom. Everything's good. Okay, the trouble is when one of these constraints becomes violated. Then you want to do a rotation or something. Okay, so when a node is not weight balanced, it's a pretty loose algorithm, but it's easy to find nodes when you should just store all the weights, store the subtree sizes, which we were doing already. You can detect when nodes are no longer weight balanced. And then we just want to weight balance it. How do we weight balance it? We rebuild the entire subtree from scratch. This is sort of the only thing we know how to do. We have a static data structure. This is a general transformation, dynamization when you have augmentation. We have this data structure. It's got all these augmented things. It's complicated. But at least it's sort of downward looking. You only need to store pointers from here down, not up. Your parent points into you, but you have a nice local thing. So if this guy's not weight balanced, if this left subtree is way heavier than the right subtree by this alpha factor, 1 over alpha factor, then just redo everything in here. Find the median, make a perfect binary search tree. Then the weights between the left and the right will be perfectly balanced. We'll have achieved the 1/2 split of weight. How long before it gets unbalanced again? A long time. If I start with a 1/2 split and then I have to get to an alpha 1 minus alpha split, it's a lot of nodes had to move from one side to the other. The alphas gets messy. So let me just say, when this happens, rebuild entire subtree. I guess it's like a half minus alpha had to move. Half minus alpha times the size of the subtree had to be inserted or deleted. That to happen, or maybe half of that. Some constant fraction. I don't really care. Alpha is a constant. I'm going to charge to the theta k updates that brought that unbalanced things. Okay, K here is the size of the subtree. Okay, so when I see a node is unbalanced, just fix it, make it perfect. And if I started out perfect, if the subtree started out perfect, I know there are theta K updates that I can charge to. The only catch is I'm actually double charging. Quite a bit, actually. If you look at, here's a tree. If I do an insert here, it makes this subtree potentially slightly unbalanced. It makes this subtree slightly unbalanced. It makes this subtree slightly unbalanced. There are log n subtrees that contain that item. Each of them may be getting worse. So if I say, well, yeah, there are these theta k updates, but actually there are log n different subtrees that will charge to the same update. So I lose a log n factor in this amortization. But it's not so bad. I get log n amortized update. This is if a rebuild costs linear time. So this is pretty nifty. I don't have to do rotations per se. I just take all the nodes in the subtree, write them down. I have them do an in-order traversal. I have them sorted. Take the median, build a nice, perfect binary search tree on those items. I can easily do that in linear time. And so this is like the brain-dead way to make this weight balance tree dynamic. The original BB alpha trees use rotations, but you don't have to. You can do this very simple thing and still get log n amortized update. And the good news is, if you have augmentation as well, because we have, with this subtree, there's tons of extra stuff, all these arrays and pointers and stuff. It's easy to build from scratch, but it's hard to maintain dynamically. Point is, now we don't have to. If ever we need to change a node, we just rebuild the entire subtree, and we can afford it at the loss of a logarithmic overhead. So we had n log to the d minus 1 n time to build the structure. So for a structure of size k, it's going to be k times log to the d minus 1 of k. We're going to lose an extra log factor. So this d minus 1 is going to turn into a d minus 2 for updates. So that was the generic structure. And now if we apply this to layered range trees, we get log to the d and amortized update. Because we had k times log to the d minus 1 of k pre-processing to rebuild the node. And just to recall, we still have log to the d minus 1 of n query. So this was regular range trees, and we've made them dynamic the same time as range trees, and still the query is a log factor faster. So for 2D, we get log n query, log squared n update, insertion and deletion of points. Any questions about that? Cool. Well, that is range searching, orthogonal range searching. Let's see. There are more results, which I don't want to cover in detail here, but I should at least know about them. And then we're going to turn to fractional cascading a little more generally. So, where is this result? Somewhere here. So for static orthogonal range searching, Range searching is a big area. We're looking at the orthogonal case. There's other versions where you're querying with a triangle or a simplex. You can query with two-sided box, which goes out to infinity here. All sorts of things are out there. But let me stick to rectangles. That's what we've seen and we can relate to. You can achieve these same bounds. Oh, sorry, no update. You can achieve the log to the d minus 1 and query using less space. So I can get log to the d minus 1 and query and n log to the d minus 1 and space, that's what we were getting before, divided by log n. Slight improvement. And in a certain model, this is basically optimal, which is kind of even crazier. This is an old result by Chazelle, 1986. Okay, this is 2D. Sorry, not 2D. It's in general. Turns out this query time is not optimal. If you allow the space to go up a little bit, you can get another log improvement. So I can get log to the d minus 2 and query if I'm willing to pay, I didn't say this is space, if I'm willing to pay n log to the d and space. So if I give up another log factor in space, I can get another log factor in query. I don't think you can keep doing that, but for one more step you can. I believe this is conjectured optimal for query. Don't know if it's proved. And this was originally done by Chazelle and Gibas using fractional cascading. And we'll see. If there's time next class, I'll show you how this works. But for now, I want to tell you in general how fractional cascading works, in generality. This is part of fractional cascading, this idea of cross-linking from a bigger structure to a smaller one, so that you don't have to keep researching, you just reuse where you were. But there's another idea. I want to show you that idea. So, fractional cascading. For d equals 2, no, it does not work. So this is for, I should say, this is for 2d and higher. D has to be bigger than 1, because you can never beat log n. Okay, so for 2d and higher, we could use the trick that we just did. For 3d and higher, you can improve by another log. Thanks. Other questions?
You can never beat log n.
We can never beat log n. In this model, which is basically comparison model, we're comparing coordinates. In that model and many other models, you can't beat log n query. Because in particular, you have to solve the search problem in 1D. So we're always hampered by that, but the question is, how does it grow with D? And the claim is we can get log n all the way up to 3 dimensions. Only at 4 dimensions do we have to pay log squared. It's pretty amazing, I think. Okay, fractional cascading. Super cool name, kind of scary name, but I was always scared of when I heard about fractional cascading. But it turns out very simple. Goal today is to not be scared. Okay. Let's start with a warm-up problem. Okay, then I'll tell you its full generality. But simple version of the problem is not geometry per se. It's kind of 1.5 dimensions, if you will. Suppose I have k lists, and each has size n. They're sorted lists, think of them. So we have n items come from an ordered universe. Here's list 1, here's list 2, here's list 3. It's k of them. Each of them has n items. I would like to search the query. We'll just do static here. Original fractional cascading was just static. These results are just static. You can make it dynamic, but there is some overhead, and I don't want to get into that. It's even messier. Or it is messy. Fractional cascading by itself is a very simple idea. Query is search for x in all lists. Okay, so I want to know what is the predecessor and successor of x in this list. I want to know what's the predecessor and successor in this list. I want to know what's the predecessor and successor in this list. All of them. There's more information. If I just merge the lists and search for x, I would find where x fits globally. But I want to know how it fits relative to this list and relative to this list and relative to this list. How do I do it? I could just do k-binary searches. So this is an easy problem to solve. You get k times log n. But now fractional cascading comes in, and we can get the optimal bound, which is k plus log n. Okay, I need k to write down the answers. I need log n to do a search in one list. It turns out I can search in all k lists simultaneously, get all k answers in k plus log n time. It's kind of cool. And actually quite easy to do. We want to use this concept. If I could search for my item for x in here, and then basically follow a pointer to where I want to go in here, I'd be done. Sadly, that can't be done. Why? Because who knows what elements are in here? All of these elements could fit right in this slot. And so how do I know where to go in this giant list? If these all fit in here, and recursively these all fit in here, then by searching up here, I learn nothing about where x fits in here. I have to do another search. And then I learn nothing about where x fits in here. So it doesn't work straight up. But if we combine this idea with fractional cascading, then we can do it. So I can erase this now. So, what do? Idea is very simple. So I'm going to call these lists L1, L2, L3 up to LK. I want to add every other item in LK to LK minus 1 and produce a new list LK minus 1 prime. Okay, so I take every second item here, just insert them into this list. Okay, it gets a constant fraction bigger. And then repeat. This is the fractional part. Here, fraction is 1/2. You can make it whatever fraction you like, less than 1. In general, I'm going to add every other item. This is in sorted order in LK, of course. That's in Li prime. The prime is the important part here. To Li minus 1 to form Li minus 1 prime. So I've got this new larger version of L2. I take half the items from here. Some of them may be items that were in L3. Some of them are items that were originally in L2. But all of them get promoted, or half of them get promoted to L1. And so I keep promoting from the bottom up. How big do my lists get? What is the size of Li prime? Well, it started with Li. And then I added half of the items that were in the next level down, Li plus 1. Okay, so this is n. And so this is going to be half of n plus half of another n plus half of, it's going to be n plus a half n plus a quarter n plus an eighth n. It's a geometric series. So this is just a constant factor growth. I'm assuming all the lists have the same size here. For simplicity, you can generalize. So I didn't really make the lists any bigger, per se. But I fixed this problem. If all of the elements in L2 fit right here in L1, it's no longer a problem because now half of the items from L2 now live in L1. So when I search among L1, I'm not quite doing a global search, but I'm finding where I fit in L1. I mean, I didn't contaminate it too much from L2. And now I can afford, or now it's useful to have pointers from L1 to L2. Let me draw a picture maybe. So, here's L1, L2, L3. So, half of the items here have been inserted into here. Now, we don't really know, maybe many of them went to near the same location. Okay, but they went there. And I'm going to have pointers in both directions. Mostly I need them down. So that if I search in here, I can figure out where I am down here. Then half of these guys, maybe I'll use another color, get promoted to the next level up. So maybe this one gets promoted, maybe this one gets promoted. I guess half, it would be that one, that one, that one, that one, that one. These guys get promoted to the next level. Okay. I claim this is enough information. This is fractional cascading in its full generality. We have the cross-linking that we had in the layered range trees, but now we also have the fractional cascading part, which is you take a fraction, you cascade it into the next layer. The cascading refers to those guys continue to get promoted. Half of them get promoted up recursively. Okay, that's where the name comes from. So now, how do we do a search? We're going to start at the top, and we're going to do a regular binary search at the top. Because we can afford log n once. So we do the binary search at the top. So maybe we find that our item fits here in this search. So that tells us, oh, well, this is where item X fits in this list. Great. Now I need to know where it fits in the next list in constant time. Well, I need some more pointers for this. So for each item in here, I'm going to store a pointer to the previous and next, let's say, red node. I mean, the previous and next node that was promoted from the list below. Okay, so now I basically know where it fits here. Not quite, because this is only half the items. So I know that it fits between this guy and this guy in list 2 prime, technically. So the only thing I don't know is it here or here? So I compare with this one item, and if this is, in general, if it's not 2, if it's not a half, if the fraction is some other constant, I spend constant time to look at a constant number of items, figure out where it fits among those items. Now I know where it fits in L2 prime. Then I follow pointers to the next items. In this case, they're the white items. So let's say it fits here, basically. I have a pointer to the previous and next white item from that item. Follow those pointers down, and now I know it's either basically here, here, here. It's somewhere in that little range of either equaling this or being between these two items or on this item or between those two items or on this item. And again, constant number of things to look at. I figure out where I belong in the primed list, which is not quite the original list. Right? Maybe I determine that X falls here. And what I really want to know is it's between this item and that item of the original list. I don't care so much about the promoted lists. So I need more pointers, which tell me if it happens that I fall here, basically every red item has a pointer to the previous, and every promoted item has a pointer to the previous and next unpromoted item from the original list. This is static. I can have all these pointers. Let's write them down. So every promoted item in Li prime, that means it came from a promotion from below. has a pointer to previous and next non-promoted item. So that's an item in Li. Okay, that's 2 pointers. And well, that's what we just used. So I found where I was among the entire L1 prime, which is almost like a global search, not quite. And then I followed these pointers to figure out where it was in the original L1. But then there was the walking down. Well, so if I found that I was in the middle of this big white region, I need to find the next red region. So it's basically the reverse. Every non-promoted item, every item in Li has a pointer. So this is basically Li prime minus Li, if you will. And then these guys need a pointer to the next and previous in that. So previous and the next item in Li prime minus Li. So these are the promoted items. These are the unpromoted items. So it's actually just 2 pointers per item. If you're promoted, you store the previous and next unpromoted. If you're unpromoted, you store the previous and next promoted. It's nice and symmetric. It's pretty clean. A lot of pointers, hard to draw, but quite simple in the end. There's 2 main ideas. One is to promote recursively up, just a constant fraction, so the lists don't get much bigger. Because it's a constant fraction, the gaps when you walk down are constant size, and so you basically get free relocalization within each list with the help of some pointers to walk down and jump left and right between the 2 colors. Okay. That's basic fractional cascading in that we solved this problem of search within k lists, each of size n, in k plus log n time, which is kind of amazing, I think. Pretty cool. But there's a more general form of this. Uses the exact same ideas, but I just want to tell you how they generalized it. This is Chazelle and Gibas. So general fractional cascading. If you look at what cascading is happening here, here being here, we essentially have a path of cascades. We start at the bottom, we push into the predecessor in the path, we push into the predecessor of the path. In the general case, we do it on a graph instead of a path, arbitrary graph. So we have a graph. The input, in some sense, you can think of this as a transformation, but it's for a specific kind of data structure. The data structure is represented by a graph, and each vertex of the graph has a set of elements. Okay, or a list of elements. That's what we had here. We had a path here, and each node in the path had a corresponding list of elements, and we wanted to search among those lists. Before I tell you exactly what search is, let me tell you about the rest of the graph. Every edge of this graph, and this is, in an ordered universe, so it's one-dimensional. Edge is labeled with a range from that ordered universe, A, B. Every edge has some range. You can think of it as a directed graph. It's probably cleaner. So it's like when I follow this edge, there's a range here. And basically, I'm only allowed to follow that edge if the range contains the thing I'm searching for. So here I was searching for some item X in all the lists. There's no ranges here, but in general, you get to specify a range. Why do we want to specify a range? We need a sort of bounded degree constraint. we want to have bounded in degree. So here we had in degree 1 for every node. In general, we don't want to have too many nodes pointing in because we want to take half the items in here, or a constant fraction of the items here, and promote them into all the nodes that point to it, so that when we follow the pointer, we get to know where we belong here. That's the general concept. So ideally, we have bounded in degree. If we do, we're done. We can have a slightly weaker condition, which is called locally bounded in degree, where the number of incoming edges for a node whose labels, the labels are ranges, the labels have to have a common intersection, x. So if we're searching for some item x, and if all the possible ways we could enter this node given item x, so this x has to fall in all those ranges, that should be bounded. Say at most some constant c. If it's always at most c for all nodes and for all x's, then this is sort of locally bounded degree. And this is these range labels help you achieve this property. Basically, if you can constrain that you're only going to follow this edge in certain situations and there aren't too many ways you could have gotten to a node, then you have this property. Contain x is a backwards containment. So x has to be, let me put it this way. I have a node with all these edges coming into it. I want x to be a valid choice for each of these edges, meaning the range, each of them is some interval on the line. All those intervals should contain x. So I'm looking at, for whatever, it's basically, if you laid out all the intervals incoming into this node, what is the maximum depth of those intervals? What's the maximum intersection between all those intervals? That is your local degree, and as long as that's a constant, you're happy. All right. So now let me specify what a search means. This is the problem that fractional cascading can solve. The goal is to find x in some k vertex sets. So k vertices, each of them has a set. I want to find x in k of them. Not all of them, k of them. That's the general problem. I have a constraint on how those sets are found. They're found by navigating this graph, starting from any vertex, and we navigate by following edges whose labels contain x. So we start at some vertex in the graph. We can follow some edges that contain x. X is a valid choice here that's inside the interval. Then from here, maybe we follow some more where x is a valid choice, and so on. Could look like anything. It doesn't have to be depth first or breadth first. It's just you follow some tree from some node where all of the edges are valid for x. At some point, you decide that I've seen enough, and now the goal is to find in this set where is x, in this set where is x, in this set where is x. Each of these sets corresponding, in each of these lists, what is the predecessor and successor of x? Question?
So is there generally some root node from which all queries start?
I believe you do not need a single root node. Each search could start from a different point.
Okay. So
But you're told where. So imagine this is like an interaction between two parties. So the input basically says, look, I'm searching for x, and I'm going to start at this node. And then the fractional cascading data structure says, OK, here's where x is in that node. Tells you immediately. Why not? Then it says, OK, I'd like to follow this edge and go to this node. And fractional cascading says, OK, here's where x is in this node in constant time. OK, then now these two guys are active, and now the adversary, the input, whatever, can decide, OK, I'm going to follow this edge or this edge. Doesn't any order. It can build this tree in any order. And every time it says, here's the edge I want to follow, the fractional cascading data structure in constant time tells you, here's where x is among all the items in that node. How does it do that? With fractional cascading. You just take half the items. Half doesn't work anymore. It now depends on that bounded in degree. But you take some function of that degree c, take some constant fraction of the items, promote them to all the things, keep going. It's a little trickier because now you have cycles. So you could actually promote back into yourself eventually by chain reactions. But if you set the constant low enough, I mean, it's like radioactive decay. You know, eventually it all goes away, right? I wish. So it's much better than radioactive decay. Radioactive is logarithmic. This is exponential. So it's decreasing very quickly. After log n steps, all your items are gone. So yeah, maybe you go in a short loop for a while. But after log n steps, it's all gone. So you're at most increasing by a log factor. In fact, you just increase by a constant factor because the number of items that remain gets so tiny very quickly. So I'm not going to go into the details, but you just take this list idea, apply it to a graph, it works. It gets messier, but in this very general scenario, you can support these searches in k plus log n, where n, let's say, is the maximum size of any vertex set. So it just directly generalizes. And this is the thing that you can use to get this log factor improvement. So, and many other things. There's actually, this was such a big thing at the time. There were 2 papers on fractional cascading, part 1 and part 2. Part 1 is what is solving this, and part 2 is applications. They solved a ton of problems that no one knew how to solve using this general fractional cascading technique. That's it for today.